Welcome back. This is Professor Holmes with Part B of the torsion formula. In Part A, we left off with an expression between the shear strain distribution in the shaft as a function of radial position, and related that to the twist angle of the shaft and the length of the shaft. What we need to do now is relate this shear strain to shear stress, and ultimately what we're after is relationship between shear stress and applied torque. So if we know the torque on the shaft, how much shear stress do we develop, and what is the shear stress distribution? All right, so let me skip through what we did in Part A. This was our ending point for Part A, and we're now in the general area of shear stress and calculation of shear stress. So again, if you look at the rod, all we're doing is essentially taking a shaft, solid or tubular, and applying torques at the ends, and we'd like to know how the shear stress distribution changes as a function of radius of the shaft. Now, from Hooke's law, remembering back to your material science courses or your strength of materials course, the shear stress is related to shear strain by proportionality constant G, which is the shear modulus. So we just apply Hooke's law, and that's equation 6 that I show here. And if we now take equation 6 and substitute it back into equation 5, so essentially we've got equation 5 from the previous lecture, and we solve now for shear stress after substituting in, we end up with equation 7a, which gives us the shear stress distribution in the shaft as a function of r. So again, that's if I were to cut a slice, or cut the shaft in half and looked at the face of the shaft. Alright, so as expected, because shear strain varies from 0 at the center of the shaft to a maximum at the outer surface, well, the shear stress had better also vary in the same way because they're related simply by this proportionality constant. Alright, so now we'll make use of this expression. Well, let's first use this to derive a maybe more convenient expression, and then we're actually going to use this expression to determine the shear stress distribution relationship to torque. Alright, tau max naturally occurs at the outer radius. That's equation 7b here. If we now divide equation 7a by 7b, and noting that g, l, and theta l are constants, then we end up with the relationship that we expected between shear stress and radius. Alright, and I plotted that here in figure 5. Where I show essentially a cross section that we've removed from the shaft, and we can better illustrate the linear distribution in shear stress in the shaft. Alright, fair enough? Okay, let's go a step further, because we still need to obtain this relationship between shear stress and torque. And I want to slow down a bit here, because this is quite important how we're going to do this. Let me first start with figure 5 here. Alright, and it shows again on the cross section the shear stress distribution. Now, just as we have internal stresses in a beam, either bending stresses or shear stresses in a beam under bending loading, we also have these internal shear stresses that develop in the material, or material elements, during torsion. So suppose that we take a small element of material here, and let's give it an area dA. Alright, and that acts at a radius, let's call it r, from the center line of the shaft. Now remember that I've got the shear stress distribution here on any material element that I might choose, and so there's shear stress that also acts on this element, tau. Alright, if I were to calculate a force, a differential force, that would be dF is tau multiplied by the area, and this now would be, let me get rid of this here, this would be a differential force. That creates an internal moment, a resisting moment on this element. So we now have this differential moment that's developed, and that's the moment arm, nothing more than r, times this dF, this differential force. Alright, now if you think about it, I've got many of these small elements of material, all right, at different radii, all right. What I want to do, that's essentially what's resisting this external applied torque, or the internal moments dm. Okay, so now let's do that once more, because that's a very important point. And so just to review, the cross section of this shaft can be divided into small area elements dA. If we multiply the shear stress by dA, and again the shear stress at a particular radial location, because it varies with radius, by this differential area dA, it gives us an internal force dF. And multiplying dF by the moment arm R gives us, I'll go back to my pen again, gives us this moment dm, differential moment dm. And so let's call that expression 8. All right, so again, this is my moment. Here I've essentially substituted back in for df, which is tau dA. Okay. Okay. Let's continue. Now, if we inspect this equation, equation 8, it shows that we're well on our way to obtaining this needed relationship between shear stress and torque. And all we have to note now, remember what I said, that all of these differential moments that are acting on these material elements are reacting to this external torque T. Okay? So all we need to do now is integrate over the cross-sectional area, and I've done that here. And let's call that equation 9a. So again, all I've done is substituted in for dm into here. All right? Now, we know what the shear stress distribution is along the radius of the shaft. So we know that that's a function of radius, so let's stick that in. And that was given by equation 7c from lecture A. And if I then factor out tau max and r naught, which are constants, I end up with this expression. So I've now got a relationship between the torque and the torque and the shear stress developed in the shaft. All right. Okay. Let's continue. In equation, we can simplify equation 9b, which I state here again at the top of the view graph. All we need to note is that this integral, if you remember back to your mathematics courses, is nothing more than the polar area moment of inertia J. All right, so all we have to do is substitute back in here, and this is J. All right. If we do that and we solve for tau max, we end up with the so-called torsion formula for a solid circular shaft, which states that the maximum shear stress developed in the shaft is nothing more than the torque times the outer radius divided by J. All right, we haven't said anything about the material in this particular formula yet. Okay, J, and you can prove it yourself. You've done this in your math courses. dA is just 2 pi r dr, and if you do the integration, you can prove to yourself that's J. All right, so for solid circular shaft under torsion, we're there, but life's not so easy, because many shafts indeed are tubular or hollow shafts. And there's a reason for that. It has to do with things such as resonant frequency, with the efficient use of material, with low mass. You want to typically to have a low mass shaft. Of course, not all shafts are going to be hollow, because it's sometimes difficult to produce a hollow shaft out of a particular material and the size you may need. And that's one of the reasons that for simple applications like electric motors, and maybe for an oil pump, a shaft in an oil pump, you might just find a standard diameter low carbon steel and utilize that. All right? But for many applications, it's much more efficient. And the reason for that is, the reason that we would rather use a tubular shaft is not only because of the low mass, but from an efficiency point of view. Remember that these differential moments that are resisting this external torque are related to the shear stress and the moment arm. And so the shear stress distribution, which I plot here for a hollow shaft, you can do this on your own, just using the same expression that we had before, but limiting it between R sub I, R inner, and R outer, the shear stress is much higher near the outer edge, near the outer radius, and therefore it's much more efficient to react into this torque. All right. So what goes on in the core of this material, if this was a solid shaft, isn't very important in terms of resisting the torque. Now, the same expression, equation 9a, can be used to obtain an expression for the maximum shear stress in a circular shaft. All right, so we've got the same expression. All we're going to do now is change our limits of integration from R sub I to R naught. Okay? And let's skip to the next view graph. So again, same derivation as before, we just changed the limit of integration from the inner radius to the outer. All right, I've repeated that expression here again from the previous view graph. All right? And now all we need to do is note that this integral, again back to our mathematics courses, this integral is the polar area moment of inertia for a hollow cross-section. Let's give that the symbol JH for hollow. And we now have an expression for the torsion formula for a tube. All right, let's give that, call that equation 10b. And again, depends upon the torque, the radius, and the polar area moment of inertia. Okay? So we made good progress now. Now let's, now, just so we can gain more insight in terms of what's going on under torsional loading, let's express for the solid circular shaft the torsion formula in terms of diameter. All right, so we just substitute in that the radius is diameter divided by 2, which I've done here. All right, and let's also use J in terms of diameters, and we end up with this expression. Now what I'd like to do is slow down for a moment. It's telling us that the maximum shear stress developed in a solid shaft, in this case, is 16 times the applied torque divided by pi times the diameter, outer diameter, to the third power. If you look at it, you say, all right, what if I've got a 1-inch diameter shaft versus a 2-inch diameter shaft? Well, because it's a cubic power, if we double the diameter from 1 inch to 2 inch, we decrease the maximum shear stress of the shaft by a factor of 8. Now that's significant because most designs, either for static loading under torsion or for fatigue loading, will depend, the lifetime or the failure will depend upon the maximum shear stress. And so we can easily get a much longer life if this is a fatigue limited application by going to larger diameters. Of course, there's other things you can do to increase fatigue, and I'll go over that in a more advanced web lecture. I've taught fatigue for many years at U of M and Georgia Tech, and now here at Bayhong. But at any rate, I'll do that in another lecture because it's very important. You can actually use the same torsion formula and analyze a problem for fatigue, a particular design. All right? Okay, let's move on. And that's the concept of torsional stiffness. And many things have torsional stiffness. An automobile has a torsional stiffness. But in terms of the rods, when we talk about torsional stiffness, what we need to do is maybe put this in a different form. Okay, our expressions. All right, so let's go back to equation 7b, which we derived in lecture A, and equation 10a, which we've just derived, the torsion formula. And let's equate those two equations and solve for the twist angle, the angle of twist of the shaft. And that expression, which I'll call equation 11, is referred to as the torsional stiffness. And that's important because for certain applications you would want high torsional stiffness, which means that when you apply the torque, you don't get very much twist. And so certainly for a robot arm, you would want high torsional stiffness as well as high bending stiffness. Okay? Now, equation 11 can be used to determine the total twist at the end of a shaft subjected to pure torsion. Remember, that's again the limitation we have. This is pure torsion. Now note, high torsional stiffness implies low twist angle. And how do we obtain that? Primarily through geometry. J is a geometric parameter. polar moment of inertia. If we increase J or increase G, the shear modulus, well, the twist angle is less, and we refer to that as a much higher torsional stiffness. Okay, so that's two ways for a given torque and length to increase torsional stiffness. Now, just to note, some textbooks, and Timoshenko is very popular, one of the very popular textbooks, and in Timoshenko's book, The Rate of Twist, he refers to the rate of twist, which is d phi dx, when solving, for example, homework problems. This rate of twist can be used to calculate the total twist angle at the end of a shaft, simply by multiplying by the length. Again, remembering back from lecture A, part A, the d phi dx under pure torsion for a circular shaft is constant. I also want to point out the angle of twist can be significant if you've got a large shaft, and so you have to be careful. In particular, if you need a precise application, or you want to limit the amount of rotational deformation. Not only can you get a lot of twisting, but that can lead to another problem, which is can lead to whipping of the shaft, or whirling problems. You have to keep that under consideration, and that's beyond the scope of this lecture. That's covered typically in mechanical design course, and there'll be a web lectures covering mechanical design, but that'll probably be 6 months from now. All right, so summarizing. I'll just leave these for you guys to read. We've got the torsion formula for solid circular shaft as well as for a hollow circular shaft. Okay. Now some general comments to wrap up this part B. You really need to go back to the derivation and the assumptions that we made and understand the implications of that when you go to design a shaft. You also need, if you were to take a course from me, and I suppose that I'm old enough now, I started teaching in '88, that some of you could actually be the sons or daughters of people I taught many years ago at Michigan. But your parents will tell you, if they had me for a class, that I would dock significantly points on an exam or homework problem if you didn't state the assumptions, or if they didn't state the assumptions. And so I expect that your professors, your current professors, expect you to do that. So clearly state all assumptions when solving a problem. The equations we derive only apply for loading below the yield strength. Again, that was one of our assumptions. Now, for thin wall tubes, we also need to worry about things such as buckling. That could occur if we have an overload, if we apply too much load, or if we have variations in the geometry or some defects. And I'll cover buckling in another teaching module, which is in mechanics of materials. These equations in general should not be applied to composite materials with continuous fibers, and that's more in the area of a laminate theory, but essentially it's because we have anisotropic material and you may get delamination between the various plies. But it's a very interesting mechanical design problem, so I'd encourage you, if you get a chance, to take a laminate theory course or a composite course. These equations should also not be applied, and this again was one of the basic assumptions we made, if we have time-dependent behavior such as creep or viscoelastic effects in the material. All right, and a few cautions. I've been a designer for quite a few years, and many of you are certainly interested in design, or you wouldn't be taking these courses. Exercise care when designing drive systems. Also, consider fatigue life. What are the implications of cyclic loading of a shaft? What about environmental effects such as corrosion? So you have to be careful when you select the material that you don't have corrosion effects. What about drive attachments? For example, if we put a pulley on a shaft, you may have a key wave. Well, certainly that's going to cause a stress concentration. If the drive attachment is a yoke that's welded on, that can cause residual stresses that you may have to worry about. So there has to be a lot of thought that goes into how I design these drive attachments. Now, related to that, the end conditions will affect the stress state. All right. So we have to worry about stress concentrations from the key wave, for example. We also have to worry about multi-axis loading. Multi-axis loading, if I take this tube again, and I apply torsion, and I apply bending at the same time, or I apply compression or tension, that's going to change the stress state. It's going to change the fatigue life. We can handle those problems. If it's a fatigue problem, we can handle that through multi-axis. fatigue theory. So it's not a big issue, and it's done every day. Otherwise, you wouldn't be able to drive a car with a drive shaft for very long. All right, so these problems have been solved, but for each application and each time you choose a material, you have to go back through and reanalyze the problem. All right, fair enough. Part C of the torsion lecture will be posted probably in about a week or so. So review parts A, part B. Email me if you have any questions, and look for part C, which are example problems. I'll solve maybe 2 or 3 example problems that are typical for undergraduate engineering, and go and run through the solutions and try to point out some of the more important aspects, for example, in choosing the proper drive shaft material or diameter. All right, good enough. Take care.